Hello, friends, engineers, developers, and professionals in the entire embedded computing space. Welcome to this Embedded Computing Design FPGA Roundtable, evolving cross platform tools for building software connected FPGA applications, sponsored by Opal Kelly. I'm Ken Briota, editor in chief for Embedded Computing Design, and I'll be your host and moderator for today's roundtable. If you're not familiar with us, please visit embeddedcomputing.com, where you will find our coverage of everything related to the design of hardware and software for embedded systems. We're chock full of design articles, white papers, blogs, videos, podcasts, and lots more, and we're always adding new content and technology coverage. In today's session, we will of course be looking at the software connected FPGA applications and lots of interesting tools for building them as we get into this roundtable discussion. Our speakers today are Steve Johnson, President and COO of Opal Kelly, and Jake Janovitz, Founder and CTO of Opal Kelly. Before we get started, let me go over just a few housekeeping items for you today. We have this entire presentation and discussion will likely take between 45 minutes and an hour. And for this series, we are inviting you to submit your questions throughout the discussion. We'll get to as many as time permits as we get to the end of each discussion topic. So get those questions in throughout the course of the presentation early and often. You'll find on the right side of your console window an area where you can enter your questions in real time. As I said, we will get to as many as we can as we go along. If we don't get to your question before we run out of time or before we need to move to the next topic, someone from Opal Kelly will get back to you with an answer as soon as they can. And if you have a technical difficulty or a question pertaining to the webinar itself, like for instance, your slides aren't advancing or there's some trouble with the audio, please put that into the question box and one of our technicians will respond as soon as they can with a fix for you. You may have to unplug it and plug it back in. On the left side of your screen, you'll see the speaker's full bios. There's a clickable tab that says handouts over there. That's how you can download a copy of the slides that are being presented today and some other material that Opal Kelly has made available for you. The on-demand version of this roundtable will be available about 24 hours after we sign off today. So if you missed something or you want to go back and review or even share it with a colleague or a friend, you can find it again through the same link that you used to sign in today. A reminder, however, that all embedded computing design webcasts are copyrighted and may not be recorded without prior permission. One last note, make sure that you check out our weekly news show in case you missed it, Embedded Insights on YouTube. It covers some of the most exciting news in the embedded computing world every Friday and every Monday as a newsletter on LinkedIn. So subscribe in both those places so you don't miss any of the news in case you missed it. I think that's enough in terms of housekeeping notes. And for me, you're here to hear the discussion. So let's get started with our very first question. Welcome, gentlemen. How are we doing today?
Great. Good to be here.
Doing great.
It's really great to have you both with us. And we're going to jump right in because I'm sure our audience is champing at the bit. You both have been working with a wide range of teams over the past 20 years across the entire embedded spectrum. Can you tell us a little bit about the type of customers that you support and the role that your solutions play in their development process these days?
Yeah, let's talk a little bit about Opal Kelly, where we came from, a little bit about our history. So we've been around a long time, been over 20 years plus, and always in the FPGA module business. So tons of experience with this stuff. What makes us a little bit different than a lot of other FPGA board vendors out there is we're not really just an eval dev board company the way that a lot of maybe Avnet. I came from Digilent, as I think some of you probably know. Opal Kelly's boards are lifecycle managed, and we look at the entire flow from sort of design prototyping all the way through to production. So it's a little bit of a different focus. Because of that, we're ISO 9000 certified, so we take seriously the kind of quality side of our business and the sort of long-term supply assurance. So that's a little bit about Opal Kelly historically. Our customers and our focus is also a little bit different than a lot of other dev board companies out there in that We service every major research university, a lot of research organizations around the world, but also a lot of commercial entities that are building products on top of our technology. A lot of them are early stage companies making scientific instrumentation, a lot of medical, biotech sorts of applications as well. So that's a little bit about our customers. Why they buy from us, they really find a way, they find our products a way to accelerate their time to market. In some ways, we're even enabling uh, products that I don't think, in some cases like this, like the company here in the middle, this quote, they don't even think they might exist without our technology. Might be overstating things a little bit, but we take pride in the fact that we're enabling customers to design products and new technologies that might be extremely difficult to do any other way. So our focus is on putting the all the power and capabilities, kind of unique capabilities of FPGAs at the end of a USB cable, often tethered to a PC, to enable the development of some pretty innovative and transformative technologies in medical imaging and scientific imaging and a lot of analytical applications, things like that. So that's a little bit about us. Jake, anything you want to add?
No, I think you summarized it pretty well there. Thanks.
Thanks.
Awesome. Thanks, guys. Remember, folks out there, if you are um, listening in and you've got a question as we go into our discussions, it would be really great for you to send in your questions because we'll get to them as they come in as best we can. But jumping back into the discussion here, Jake, Steve, what are the biggest challenges teams face when bringing FPGAs into a product? And how are modern tools helping address those gaps? Do these workflows realistically shorten time to market? Are they mainly about developer convenience? What's driving those decisions?
Yeah, so I can take this one, Steve. As you introduced there, our customers generally know that FPGAs are an important part of the solution that they're looking to provide, but they may not necessarily have the expertise or the knowledge to perform that integration, or they simply don't want to maintain that component of their expertise. They have a particular value proposition that they're trying to put forth to their customers, and they're hiring expertise in that area, and they don't really want to spread too thin. In particular, they might have expertise in the sensing or the interface hardware that they're building in the analytical software side, but what lies between the hardware and the software isn't their core competency. Our products provide a solution for the data transport aspect as well as the hardware design. And so we take the data from the hardware that they've designed through our modules and to the software side. And so packaging the module and abstracting that data transport gives our customers access to the capabilities of the FPGA within their larger system without the distractions of building and maintaining that piece of hardware. As for your last question, I think this definitely reduces time to market. We saw in some of the quotes from existing customers that any additional piece of hardware or software component in a system is some sort of risk, and any risk that isn't part of the core value proposition is something that they would like to avoid.
Yeah, that sort of that developer time and everything is such a game of inches and slivers of time. Every little bit seems to help. Although I guess keeping your developers happy and making things a little more convenient and easier is not a bad play either.
True.
I think we'll move right along here to our next question. Reminder to you folks out there watching, get those questions in. We'll answer them as they come in as best we can. So I want to see your questions as they roll through. Now, this is one that I've been really looking forward to picking your brain on, guys. How is the shift away from HDL-centric workflows reshaping the profile of a typical FPGA developer? I mean, where are you seeing the limits of abstraction? When does a developer still need to work at the HDL level? Is it just higher up than that now?
Yeah, so I, I came from working at National Instruments. I was there over 20 years, and some of you out there probably know that. And I put been a big effort going into essentially making FPGAs a core part of their kind of test and measurement platform, with the development of LabVIEW FPGA. And of course, that was one of these efforts, right? It was a big effort to try and open up the capabilities of FPGAs to an audience that typically wasn't an embedded systems developer, but maybe a test and measurement professional, someone doing R&D, and that was very data acquisition or control centric, and trying to put the capabilities of the FPGA in their hands. That was one attempt at it. We've seen others. MATLAB HDL coder is an example of another way of essentially trying to loop in another set of developers, often scientists, mathematicians, other folks that are maybe looking to implement algorithms that they're developing in an entirely different environment, but to actually try and run them in real time with real data. And so these are different attempts at essentially trying to, again, exploit the capabilities of FPGAs, the unique capabilities of FPGAs, and their inherent parallelism, which you don't get with a microprocessor-based system. And then the other area we've seen FPGAs being used is in machine learning and AI applications, where again the inherent sort of capabilities, fabric, design, architecture of FPGA lends itself to some of the sort of neural net kind of models that form the kind of core of a lot of the early machine learning research. So all of that stuff has been really interesting to watch. In our world, there's where we're very hardware centric, and that we're often trying to bridge, as Jake was talking about, we're bridging often from A to D, D to A converters, various unique bespoke hardware that the customer is trying to interface from the kind of the business end of their machinery or analytical system or imaging system. Their R&D dollars tend to be put on that end of things, and then the other part of it is at the PC side, where they want to do visualization, or they want to apply algorithms that are not appropriate maybe to try and deploy on an FPGA. So we're in the middle, and we find that the limits of abstraction here, those types of tools aren't all that useful when you're trying to design a high bandwidth interface to an A to D converter. That typically has to be kind of carefully designed at the hardware level, it's a pin level, at the understanding the specifications of the device itself. So that's how I would answer this question. Jake, do you have anything else to add to that?
Yeah, I mean, I think there's always going to be a place for HDL in these designs. I think if we look to the software abstraction over the last 50, 60, 70 years, you see kind of similar trends. You've got assembly level software is still in use today, but it's relatively minimal. We've built remarkable levels of abstraction in software, all the way to virtualizing the machine, and then having virtual machines run on top of a virtualized machine and ad nauseum. And so there's a lot of usefulness to that as the CPU power increases dramatically and developers are more in a crunch to do things faster. Today, I think we're seeing primarily high-level synthesis, HLS, and modularization on top of like AXI bus is the primary levels that we're seeing right now. But it's I think we're only scratching the surface at this point of how we're abstracting the levels of hardware design. But as you said, at the sensor level or at the interface level, there's going to be a consistent level of requirement for HDLs.
Yeah, it's interesting. This HDL shift didn't seem like a really big deal, and yet it really is influencing design in a really broad spectrum of ways, I feel like. So this is a great topic. I mean, this isn't one of our questions, but I'm curious. I mean, down the road, do you think? I mean, you say HDL, there's always going to be a place for it, but do you think that it gets replaced with newer technology? Do you think that there's there is a shift, uh, in evolution, especially with more and more integrated machine learning and AI tools and things like that? Do you think that is coming down the line at some point?
I don't personally see that happening anytime soon. I think the way we develop that level of interface is changing. We see, for example, artificial intelligence, generative AI as producing an awful lot of the HDL. Just the other day, I asked an AI to produce a full image pipeline, and it was able to do the whole thing within a couple of minutes. And it's not tested. There's a lot of I'm sure there's a lot of human intervention that's still involved in that, but the fact that it could build that from soup to nuts within a couple of minutes is pretty remarkable. And so somehow the hardware has to operate. We still have analog interfaces on the edges of a digital interface. So somebody has to do that design. I think it's just being pushed to the fringes more.
Yeah. I'm not gonna take the bait and let myself to get distracted and change this into a debate about generative AI code. But I have a whole article about the copyright implications there and the patenting implications.
I have no
I'm
idea who wrote the generative AI that I actually pulled from it. So that's a big question.
So go over to embeddedcomputing.com if you want to read my unhinged opinions. We do have a question from our audience out here, which is simple and straightforward. What about bootloader? So obviously they're wondering what the implications of bootloader would be in this whole discussion. So I figure I'll float that to you guys.
I'm not sure what he means. Jake, do you get that?
I do not. Sorry. Unfamiliar with
Yeah,
bootloader.
we'll need a little bit more
Yeah.
context, I think. To
If
help
you
out with that.
submitted that question, I'm not going to read your name out loud, but give us some more detail. We'll come back around to it
Yeah.
because I'm interested to hear what it is that you're looking for specifically. In the meantime, I'm going to take us to our next question here. What advantages do abstracted communication layers bring compared to traditional tool chains? How do runtime architectures balance performance with flexibility? The abstracted communication layer is such a fascinating space, so feel free to expand here, but I'd love to hear what you have to say.
Yes, I think for our product, we have abstracted that communication layer in one way or another for the last 20 years. And for us, it's all about productivity for the engineer, trying to take away a piece of the design that isn't particularly sexy or interesting for them to work on, and commoditizing it. And what they can do with our product is they just plug it in like they plug in some other chip, and they can use that layer of communication without knowing anything about USB or PCI Express or Ethernet in some cases, and shove data down a pipe and get it on the other side. So for our customers, it's really about solving problems that they don't want to focus on. The abstraction of that, I think, is not necessarily part of the important aspect of it. It just kind of comes along with the fact that we've put a layer on top of USB that they don't have to handle. As for runtime architectures, our products communicate between an FPGA and the hardware system behind it, and the PC or some sort of a CPU resource. And so again, for our customers, the important thing is that they can use the FPGA for interface functionality, or some of the very high highly efficient, very fast front-end processing that the FPGA does really well. And then they can offload the more complex processing that doesn't fit the FPGA strengths to a CPU and to benefit from that architecture. And then these days to make that jump into connectivity to cloud or other devices on the network.
Awesome. I love the idea of this sort of, here's a layer that you never have to worry about. That's just going to work all the time. You do the thing that you want to work on, and we've handled this abstracted layer and everything. It's almost a building blocks kind of approach, which I think is really it's really addressing some of the big challenges that engineers and developers face, where they're being asked to be good at everything instead of focusing on the thing that they want to do. Years ago, I saw a similar trend happen in the IoT space, where a lot of the folks were being asked, systems integrators and stuff were being asked to just create everything from scratch, and slowly but surely, they were given tools that allowed them to do more. It's not quite an analog, but plug and play kind of operations. And I assume that you guys find that too, where you're able to talk to customers about this is going to be a lot simpler for you.
Yeah, well, that's there are a couple of other areas where we're starting to apply that same kind of principle. And absolutely, as the technology has become more complex and the engineers are being expected to deal with new standards and also, of course, to be doing more with less, right? Doing more system level design with fewer and fewer, resources and not necessarily having the expertise on their teams to deal with some of this kind of technology. The more we can do to sort of modularize or componentize and abstract some of these core enabling technologies, that's a big advantage, right? So the other one is that we'll touch on a little bit is the sort of ADC DAC, sensor interface to the FPGA. That area, one of the ways that the FMC bus, the FPGA mezzanine sort of standard, that's been around a long time. It's a big, expensive interface. It works pretty well for larger systems. It has a sort of a pin count approach that matches well with FPGAs, but it's often overkill for the kinds of systems that our customers are developing. And so Opal Kelly introduced a standard called syzygy, which fits between the small pin count standards that you might see like PMOD or microclick, things like that, up and between FMC. And the syzygy standard is a kind of a nice in between and allows our customers. You'll notice on most Opal Kelly boards there are syzygy expansion ports, and those are meant to in many ways to do the same thing you're talking about, which is, all right, let's just make it easy for a customer to add an ADC or a DAC or some kind of a sensor, plug it into the board. It's an open standard. We freely license it, and that's one of the things that we're going to be pushing more into. We'll talk a little bit and show some examples of this in a little bit, but it's another example of us trying to essentially make the system level design easier for engineers that are already strapped, right, and
Yeah.
don't necessarily have the expertise to do a high speed interconnect standard and design one in-house just for their own needs. So
Right.
another example like
Yeah,
that.
I need this solution in 2 weeks, but in the meantime, can you please engineer an entirely new protocol on the way?
Right. Well, the other thing too that these standards do for our customers is we're also pushing the USB bandwidth up, right, from USB 3 into the 3.2 standards, and so
Right.
going from 3-ish gigabytes per second to 10, 20 gigabits per second. So pushing up into the newer 3.2 standards. And so that's another thing. We abstract that whole problem from a customer that's adopted our technology and our front panel, this abstraction that we were talking about. So, so you get essentially for free, you get to just tag on to the development we're doing to push the bandwidths up as well, which has been a big request from our customers, is
Oh, I
to
believe
provide
that.
an even higher bandwidth to the FPGA.
Oh, yeah. Absolutely, I believe that. Um, Jake, I don't know if Steve and I have been chatting for a minute here. I don't know if you wanted to add anything to this part of the discussion.
No. Carry on, Steve.
Awesome. All right, well then let's move ahead and see here. All right. So as this ongoing wave of abstraction continues to reshape and democratize FPGA development, how is Opal Kelly contributing to that shift?
Yeah, so actually, we're maybe a little bit ahead. I brought up syzygy. That was an example of this, and we're again looking at the patterns of the kind of architectures that our customers are building around. We're looking at the sort of system level again. Is like, how can we take that entire application pattern that we see again and again with some kind of high-speed data acquisition system or control system, the FPGA being the appropriate and best technology to interface with those sensors, actuators, implement either localized control systems on the FPGA or in many cases data reduction algorithms or calibration kinds of schemes, and then essentially getting data back to the FPGA, back to the PC side for further processing and visualization. That model, that's what we're looking at, that entire system. And as we push forward, the investments we're making right now are across that entire kind of application model. So we'll get into what's now. We're in beta now of this technology, our latest version of FrontPanel, which incorporates all three of those elements. It incorporates the IP that we make available for the FPGA to implement the high bandwidth USB interface, the connections to the FPGA that allow the customer to essentially get data into their design, and then the host side software APIs that allow a customer to develop host side software and move data back and forth between the PC and the FPGA efficiently. So so let's get to the. I guess I can. Yeah, we go. Thanks. So this is a picture of this application pattern that we focus on, and you can see on the left side here the host PC side. So as I mentioned, we're working on all elements of this whole architecture right now, and on the right side, on the FPGA side, the investments we're making there to make sure that the latest generation of AMD Xilinx devices are being, we're making the best of those latest generation parts. And then that's the HDL part of the solution we provide with our boards. Excuse me. And then we provide an API, as on the left side, you can see that allows customers to move the data back and forth efficiently. I think what we're most excited to talk about, though, today is the host side software development. In most cases, our customers have to develop some kind of software to allow a useful, productive user interface and visualization of data. And so our big work there, I think the most exciting part of it and the most visible side of what we've been working on is with the FrontPanel API side of things. So let's go to the next slide.
Yeah,
So Jake, why don't you talk to this? Yeah.
Yeah, sure. Yeah, so as Steve mentioned, we're focused on the system design aspect and how to allow customers to be productive on a software connected FPGA application. Traditionally, our SDK provided just an API, a multi-platform, multilingual API in typically C++ or C# or Python. And then it was the customer's responsibility to bring whatever application to life that they needed. And more recently, I think the whole world has kind of witnessed the proliferation of the JavaScript, HTML, CSS sort of application development side. And not only is that currently being seen with cloud-based applications, but it's also being deployed as a desktop-based type environment. And there's a lot of good arguments for that. And I think the environment is kind of one of the most popular development environments of the world now, and it's quickly dwarfed previous like C++ development. So what we've done with FrontPanel 6 is develop that on top of essentially a browser using Electron. So if you haven't heard of Electron, it's a way that cloud-based companies have deployed a desktop native sort of application that feels like a desktop application, but it's really running in the JavaScript environment. It's just a very fast way to develop applications that provide a GUI. And so we've tapped into that with FrontPanel 6, and we've kind of pushed the boundary from just the API and the SDK into a GUI environment that customers can deploy a full application on. Currently, it's in beta, and we wanted to eventually build a development space that is cross-platform and widely supported. And this environment of the browser has made that possible for us. And so that's where we are on that. Do we have another slide on that? Yeah, so this is just a slide that shows a few of the example applications we've built. Really simple stuff on the left is the counters. It's kind of a first encounter with FrontPanel 6 and working with the communication protocol between the FPGA and the software. And we've got a couple of very simple examples there. But with SysG peripherals and the capabilities of FPGAs today, we quickly build something like a signal generator and a spectrum visualizer just with off-the-shelf components, and put this together using a variety of plugins that come from the JavaScript community that are all freely available. And it's a very good, rapid development cycle for pretty functional applications all the way to fully production ready applications. This example didn't take our developers very long to put together. The charting wasn't anything custom. It's just off the shelf and relatively high performant for the space that it's in. And then the backend FPGA development is also pretty easy. There's off-the-shelf FFT cores and Cordic cores for signal generation and all sorts of things that make a lot of this development very fast. And this is something that we couldn't really deploy 10 years ago as easily because there hadn't been a stabilization of the software development side as much as there is today. So deploying this allows us to develop for the three major software platforms, Linux, Mac OS, and Windows, without any portability concerns at all. And the development environment itself is world-class. So I think that's kind of what we're doing to proliferate this environment a little bit and make it easier for our customers to build very functional applications without too much effort.
And so on the hardware side, to simplify the setup and development and just start to use more of this technology, some of the technology you've been talking about, including this syzygy expansion, IO expansion standard, we're developing what we're calling syzygy hubs at this point. These are essentially the smallest incarnation of and simplest incarnation of the architecture, this pattern that we've been talking about of a host PC USB interface to an FPGA, then broken out to an I/O system. So the Syzygy Hub Pro here that we're showing here is in development right now. You can see here it's incorporates an Arctic UltraScale Plus FPGA USB-C interface on it, and with power delivery, so power over USB, so no separate power supply needed. And then it has three Syzygy standard ports on it for I/O expansion. We have a product line of these Syzygy I/O modules, including A to D, D to A, some communications style, debug style, digital I/O stuff, and other companies make them too. So we'll be developing this product line out further, the I/O expansion as well, and trying to make this whole sort of this whole sort of system integration problem that we've been talking about today even that much simpler for you to get started with, and get going with the software development as well. So we're making aligned with this event today. We're doing a 10% off if we get you signed up for this. We're going to do like a coupon code so that you can get one of these hubs at a discount and start to experience this whole design flow that we've been talking about today yourself. So yeah, that's kind of where we are today. We're super excited about how far we've come. This has been something that I think, Jake, you've been talking about this software development side of things now for a couple of years. So we're just really excited that we're at the point where we're sort of ready to get it out into the wild.
Yeah, definitely.
Yeah, that's really, really cool. It's the open protocol for Syzygy is really a great offering to the industry, and I always love to see that kind of thing happen because it's a service for everybody who's working and trying to build stuff. And we have a couple of questions here from the crowd, so I want to jump into those before we start wrapping up here. Here's one. What type of real world applications do you see being a good fit for the Hub platform?
Yeah, I think right off the top, data acquisition sorts of applications is kind of the obvious ones, right? You plug in what you see there, that in this image, the bottom and top plugin modules are representing dual channel A to D and D to A modules. So very typical for customers to essentially be designing and implementing a scope-like kind of data acquisition system. Usually a scope itself is not either form factor appropriate or is too constrained in terms of what kind of processing can be done in a scope in real time. So essentially, some kind of customized data acquisition system where you're acquiring data from some kind of a sensor. It could be a photo multiplier tube or something like this, often used in imaging or scientific analytical applications. Some kind of processing done on the FPGA, sort of pre-processing of that sensor data, and then pushing that data over USB up to the host PC for sort of visualization, further processing and visualization. That's a very common application model. Another would be a control system where you need high-speed control in like a photonics application of positioning systems, mirrors, and laser based control. The control loop itself typically needs to happen down near the hardware, down near the sensors and actuators, so on the FPGA. on the FPGA, you have a inherently low jitter, high bandwidth control environment, where you can run your PID or other control schemes in hardware, and isolated from all the uncertainties of the PC environment, the determinism and problems that you would have on the PC side. So that's another very common application of using FPGA out at the end of a USB cable. And then the USB cable is providing command and control to that control system at the end of the cable. So those are a couple examples of typical applications.
And Steve, I could chime in with a really common one for our customers is either semiconductor evaluation or verification and validation. So we see a lot of customers who get new silicon back or a system back, and they use our system to communicate with that system just to do validation of what they've been building, or in end-of-line testing and production to do verification and validation there for thousands of units or whatever they're building as part of an integrated system to have just an automation for test and measurement on that system.
Right. Again, yeah, it's way more cost effective to make multiples of these little custom IO systems for doing that kind of test and verification than to essentially put a stack of benchtop instruments up just for some kind of a V&V application or end-of-line test application.
Yeah, for sure.
Yeah.
Well, as we get close to the end of our time here, gentlemen, my rule is always to give you the final word. Although I'm going to cheat at the end with some more housekeeping. So, is there anything that we didn't talk about in the world of software FPGA applications and the meeting of the two that you really think that you'd like to leave our audience with today? And make sure you remind them about the special offer here with FrontPanel 6 and Syzygy.
Well, you've just done that for us. Thank you. No, I mean, I guess from my side, we've talked a lot about where we're going. I would encourage people to take a look at our website and see the full range of products that we make. I do want to emphasize that unlike, again, a lot of FPGA board companies out there, we're focused on the entire problem, from the R&D and the sort of rapid prototyping that we've been talking about a lot today, all the way through to life cycle managed boards that often we continue to ship boards that were developed, designed, and first manufactured over 10 years ago. And so we're a reliable partner and supplier to companies that are making that essentially are banking on us being around because they're building on top of our technology. So I just wanted to emphasize that.
Yeah.
And I would say just one. Download the FrontPanel 6 beta. It's available now. We've still got a little bit more work to do on it, but it's really exciting to be able to have a full environment provided by the browser environment to develop the final leg of that application. It's pretty exciting to see that happen.
Are you guys still taking user notes as they mess around in the beta?
Oh yeah, of course, always.
Yeah, awesome. All right. Well, then I think we will move to our end notes here. Folks out there who are watching, I'm afraid that is just about the end of our time. If we didn't get to your question or you didn't get a chance to submit it, one of the folks from Opal Kelly will be in touch as soon as they can. Please feel free to keep reaching out with questions and to get involved with the open beta. Remember, you are going to receive a link to the archive of this discussion and presentation, so you can view it all again later and check it out. I'd like to thank Steve and Jake for the great discussion. This was really insightful, really cool. I love to see the direction that FPGA is going in general and how widespread it's really becoming. Not sure anybody would have predicted that 15 years ago. And thanks to Opal Kelly for sponsoring this event. Of course, none of these things would be possible without all of you out there watching and listening, the engineers and developers and embedded computing pros who are building all this stuff that we're trying to put out there in the world. Make sure you check out embeddedcomputing.com for all the news that you need to know as you're going through your day-to-day. And don't forget to check out Opal Kelly and FrontPanel 6. Once again, thanks very much, Steve. Thank you, Jake, for joining me today.
Thanks, Ken.
Thank you. Yeah.
Really appreciate you all, and thank you all for attending. Have a great day.